I was taking a look at the official ClickHouse definition, and it says, I'm going to read it literally, ClickHouse is a high-performance column-oriented SQL database management system, DBMS, for online analytical processing, OLAP. Let's take a breath. Yeah, it's too long. It says too many things, but it misses one important thing, which is its distributed nature. So in this video, I'm going to introduce the basic distributed architecture of ClickHouse and the most important thing, which are the different layers of complexity it introduces when you want to integrate it into your existing system for analytical use cases. Let's start by taking a look at this diagram. Usually when you configure ClickHouse, a ClickHouse cluster, you have different ClickHouse servers configured as replicas. Optionally, you can do sharding. When you do sharding, you have multiple replicas for each shard. I'm gonna go with a basic, very basic architecture. For instance, you may have 2, 3 replicas just to start. Once you add replicas, you need some component for coordination among replicas. Usually you use Zookeeper, configuring 3 nodes servers. And for storage, you can go local, not recommended, not cost effective. You can go cloud storage, very cost effective, compute storage separation, or you can go hybrid, which is using cloud storage together with a local disk as a cache. The way coordination happens is through Zookeeper. So for instance, let me open this screen. Whenever you create a table, let's say you create it in one of the replicas, and this replica announces in some queue in Zookeeper that a new table has been created. This is a DDL queue, and the other replicas are constantly polling this queue. Just to learn, they have to perform some operation, okay, in the replicas. You configure everything with XML. So this is the cluster configuration for this architecture. You have Zookeeper with 3 nodes. You have the remote servers, 1 single shard, 3 replicas. Whenever you want to add a new replica, then you can add it to this list. And for storage, you can have both local or cloud storage disks, and then you define a policy in which you are using the local disk as a cache, the cloud storage as cold storage, and you define some factor whenever the disk is about to be completely filled, in this case 80%, then data is moved to the cloud. Okay, so we have seen how setting up a ClickHouse cluster is fairly easy, but the hard part is keeping it running. Okay, so you may have spikes in reads, you may have heavy queries, you may have write peaks, ingestion peaks, and you have to learn to detect some of those scenarios and learn to scale the cluster for. So let's see some of those specific scenarios. Okay, reads. There are at least 3 scenarios you're gonna face. There are real-time queries. They happen, a lot of them at the same time, and you want them to be fast. Then you have long-running queries. This is the kind of queries that can take several seconds or minutes. They are pretty memory-intensive operations because they are scanning a lot of data. And then we have like the very, very long-running queries. These are queries that can take hours or even days. For instance, a data migration, even when it's a write operation as well, a data migration has to process a lot of data. And in these cases, you usually want specific strategy and you have specific compute resources to tackle these requests. To tackle some of these scenarios, you usually introduce a load balancer into your architecture. So you have your ClickHouse cluster, your system, your backend, your application, whatever. And you have a load balancer that handles connections to the cluster and can do some basic routing, okay? So whenever you have a new request, it can be route to a different replica each time, so the load is balanced in that way, okay? When you face high concurrency scenario, if you need, you can add more replicas to the cluster and continue using them to support the load, okay? For low latency scenarios, when the cluster can't cope with the load, what you can do is have beefier machines. Usually latency is linear with the compute resources, so you can assign more threads to each query and they will be usually faster. There are other strategies we already mentioned. There is sharding. This is a more complicated way to solve this problem, but another way is using parallel replicas, which is a feature of ClickHouse in which you can route a query to a specific replica, and this is going to delegate to the rest of replicas or a subset of them to complete the request. One important thing to mention is you usually need more than just a load balancer, because your backend, your application, your system has to know about the cluster health. Because it's not just that the router does everything, but your backend in some occasions need to hint the requests so the load balancer knows what to do with them. So whenever you have, for instance, long-running queries, you may want to mark them so the load balancer knows that they have to go to a very specific replica, okay? This is a good strategy when you have long-running queries that you want to run on specific compute resources. And it's a simple way to achieve compute separation. So you might have your real-time queries running, for instance, in these two replicas. And if you want to do like a backfill or a data migration that is going to take 30 hours because it's going to rewrite your complete data layout, then you can use specific resources with other strategies we will see in these videos, okay? Ingestion is a totally different beast, and to understand ingestion, there are 5 concepts that are important to understand: how inserts work, especially the immutable parts mechanism that ClickHouse has implemented, merges, reads, mutations, and the importance of the table design. Okay, let's see an example. Let's say we have this table: timestamp, ID, user ID, event type, properties. But the important part is this one. Let me annotate it. Partition, okay? Partition by month. Now, let's say we're going to insert these 4 rows. And look at this. We have 2 rows in September and 2 rows in August, okay? So, what is going to happen? You're going to send this insert to ClickHouse, and ClickHouse is going to optimize the insert, and it's going to write 2 parts, 1 on each partition. Okay, we have 2 rows in September, 2 rows in August. Whenever you insert some data, it detects the partition key, it creates a part, and it writes this to disk. Then there is a secondary process that runs in the background, which takes smaller parts. Let's say you have other parts from other inserts, and it's going to merge them into bigger parts, because this is going to optimize reads. The parts that got merged, they are marked as inactive, and eventually they are garbage collected. And on the other hand, there is other operations, which is called mutations, which is triggered by certain operations. For instance, whenever you do an update or a delete, what ClickHouse is going to do is going to take the parts involved in the update or delete, it's going to mutate them, deleting or updating the necessary rows, and create another part, okay? So this is the immutable parts mechanism of ClickHouse. So we've seen how inserts work in ClickHouse and how these 5 concepts, inserts and parts, merge, reads, table design, and mutations are related. And there is a balance you have to find when ingesting in ClickHouse. On one hand, you want larger parts for reads, but the larger they are, it's more expensive merging them. So you might think, okay, so let's ingest just bigger batches, so it's not necessary to do so many merges. But then you are increasing latency and you're going to need more memory to ingest that data. And last but not least, you need to be aware that schema and partitioning design is important, because imagine you partition by timestamp and you ingest 1 million rows for different timestamps. What ClickHouse is going to do is going to write a part for each partition key, which is going to be each timestamp. So you're going to have like 1 million parts. This is a very classical problem in ClickHouse that can take the cluster down, okay? There is another hidden problem, because since ClickHouse by design writes immutable parts, schema and especially partitioning is immutable and changing it is hard. So taking into account these three things, the balance is really hard to achieve, okay? What do you do in these cases? You want to find that balance on having fewer parts of a right size, so you don't have problems in your cluster when ingesting at high throughput. You end up building an ingestion proxy that it takes to buffer some data and build those parts, okay? It also can take other responsibilities, like having back pressure mechanisms when merges are getting slower than inserts, or have a queue when you have an ingestion peak and you want to hold the data while you scale the cluster, and other failover mechanisms that are not implemented in ClickHouse. What happens when the cluster is down? Do you want to lose that data, or do you want to have a mechanism so you can replay it later, okay? Usually, this is implemented as another component in your stack that takes care of all that ingestion. It goes through the load balancer, because in the same way that you route the reads, you can also route the writes to a specific replica that just takes care of inserts. And also mention that sometimes you can replace that like specific or custom component with some Kafka actually. But it depends. I mean, there is trade-offs, of course. It depends on your use case, your architecture, because this has a specific protocol. It cannot, depending on your architecture, it can be cost effective or not. You might prefer something ad hoc. So this is one of the problems you might face when ingesting in ClickHouse at scale. This is a summary of the scaling strategies you may face when operating ClickHouse. You want to reduce latency, you need more computing, you can do vertical scaling. You want to scale concurrency, you can add more replicas, horizontal scaling. You want to scale ingestion, you can have a dedicated proxy for it. You want to scale reads, you need a load balancer and some component that coordinates the different requests or queries you want to do depending on the use case to different replicas or compute resources. And then remember, schema and query design are important, both for ingestion and selection. Let's talk about other complexity layers in ClickHouse. These are usually hidden, and you don't know about them until you have to operate it. And that's specifically it. ClickHouse is an operational monster. It has it has literally hundreds of system tables, and you have to know some of them to debug, to monitor the cluster. And there is like more than 1,000 settings you can tweak to have more performance, to enable feature flags, to control how parts are ingested. And you have to know them both individually and the conflicts they may have between them, okay? Other things you have to take into account, upgrades, okay? The open source version of ClickHouse makes a minor release every month. And a fun fact is that they use year a month for the release version. Upgrades don't have to be necessarily complex, but they might be. At least you cannot just trust on upgrading a version and that's it. You have to have a mechanism for it. We can talk about this in later episodes. And it's important to know that given that complexity on upgrades and operations, you might need a dedicated team, an expert dedicated team that knows about those internals, okay? Another thing to mention is, apart from having a dedicated infra team, you are going to need a data team because ClickHouse internals are very tricky. And we've talked about scalability in ClickHouse, but most of the times you achieve scalability not adding more infrastructure, but solving data engineering problems, okay? And this is what specifically data engineers do. They do pipelines, they do schema and data modeling, which in ClickHouse is very relevant. They know how to run and orchestrate complex data workflows, data quality, governance, etc. And because they are data engineers, they usually don't have the tools, or they don't have the skills, or they don't have the way, because the product is where what they are managing is different, to apply the same practices that developers do. They usually don't do version control, testing, continuous integration, or they don't have a way to do local development, okay? So you end up having a coordination problem between teams. So you have now 3 teams to coordinate: infra, data, and product. They have different responsibilities. They have different tools, workflows, life cycles. And whenever you as a product engineer that is used to deliver like every day, several times per day, you need to deploy a new analytics use case, and imagine the feature you need, it's not in your ClickHouse cluster in production. Well, you may need to do an upgrade, which can take hours, days, weeks, it depends. Or if you need a specific new materialized view that solves a use case or that optimizes it, you might need help from the data team. And this can take hours to implement, but days to bring to production, depending on the size of your tables, okay? And if you think about it, about how developers used to work, I like to call DevX not as a developer experience, but developer expectations. So what do developers and software engineers expect when they work or when they build a product? They want, or they expect, local development. They usually are used to deploy stateless apps, and database deployment is completely different. It's another paradigm. Life cycle is completely different. And ideally, they are fine with SQL. They sometimes use abstractions on top of it. But what they don't expect is having specific ClickHouse expertise. It's fine that you learn about it, but ideally you want a more straightforward way to interact with your database, okay? So yeah, there is something nice about ClickHouse, that is that being open source, there is a nice ecosystem around it. But in my opinion, there are 3 things that doesn't make it super great. First is sometimes it's hard to find the right tool for the job. You may see lots of GitHub repos with tools from solo developers that solve specific issue and you cannot use because they are abandoned. For the projects that are actually maintained, you might find you need like a lot of different tools for your day-to-day job. You need some library as a client to do requests. You may need another for data migrations. You may need one tool as an ORM if you want to use it, or to handle schemas. Then you may need another for database management or introspection, another for observability. So things start to get complicated. And if you take a look at the ecosystem, it's very data engineering centric. Sometimes it's look like the creators haven't dog-fooded their tools. It's like, okay, we have an ORM, let's do a plugin for ClickHouse. But does it make sense? I don't know, because I don't use it. I'm not solving any problem. I'm just adding another layer on top of my product, okay? So this is some of the challenges we've been talking about in this video. ClickHouse is a database. Yes, it is. It's the de facto standard for real-time analytics. Probably yes. It is battle tested. Yes, but it comes with different layers of complexity. It's a distributed system. Scaling is not necessarily easy. You have the problem that it's complex. So you're gonna need different teams for the different layers. And developers expect to work with database in a very different way that it is right now. In this series of videos, we're gonna talk about ClickHouse from the point of view of a developer. We've already mentioned of the different layers of complexity of ClickHouse, but the good news is all of them can be abstracted, so you can focus on the important parts, and this is what we're going to explain. You're going to learn about schema design, about engines, indexing, query optimization, materialized views, and all the specific functions in SQL that help you build analytics products. You can find in the description all the materials for this presentation, and subscribe for more.